you've made some measurements, you've associated uncertainties with those measurements, and now, because of what you need to do in the lab or experiment or what you've been asked to do, you need to combine those numbers. So the question is, how do I, say, multiply two numbers together that have uncertainties associated with them? How are those uncertainties going to combine? Okay, that dynamic is called error propagation because you're taking fuzzy measurements and combining them with other fuzzy measurements, so to speak. It turns out that there's two ways to express error. One is called the absolute uncertainty, and the other is called the fractional or relative uncertainty. So if you take a look on the screen, I've written them out as they are. Okay, so on the left, okay, you see an example of a measurement that was made, 5.5 plus or minus 0.1 centimeters. That 0.1 centimeters is called the absolute uncertainty. Okay, it's an actual number. On the right, you see that the value of the absolute uncertainty is compared to the measurement that it's associated with, right? So over here, right, this is a comparison. And the reason that comparison is helpful is sometimes the same absolute uncertainty can mean very different things when you compare it to the measurement. Look at the number underneath. What if we had the same absolute uncertainty, but the actual value was very different? Watch what that's going to look like over here. You're going to see that this can mean a very different thing. Okay. When you do this fraction out here, it comes out to 0.018, right? When you do this fraction here, it comes out to 1. Now, it's often more convenient to work in percents rather than fractions. So if we write these out down here, it'd be 5.5 plus or minus 18% versus 0.1 plus or minus 100%. So you see the difference there, right? I think you realize you would not be very confident of a measurement if you had 100% error. So even though the absolute uncertainty between these two measurements is the same, when compared to the measurements that they're connected to, it's a vastly different precision. Like you couldn't say that, oh, I only have 0.1 error, that's really good. Well, 0.1 is only really good when you're comparing it to a relatively large number, right? 0.1 of 5.5 is only 18%, or excuse me, 1.8%. 1.8%. Here we go. Yeah. Whereas 0.1 compared to 0.1 is a huge error, right? So sometimes it's more practical and more meaningful to go with a fractional versus an absolute uncertainty. All right, so now that you understand that, we're ready to combine some numbers. And it turns out that the rules are different depending on how you're combining them mathematically, right? So for example, if you're multiplying, the rules are different than if you're adding or subtracting. So let's look at the addition subtraction rules first. So here is an example of adding two numbers with uncertainties, okay, right here. And I want to know what's this going to come out to when I actually add them up. What am I going to do with the uncertainties? Well, it's a pretty easy rule because guess what? If you add the numbers, you add the uncertainties, right? When you add the numbers, you add the uncertainties. The same thing would go here for subtraction. It turns out that if you subtract these two numbers, you're still going to end up adding the uncertainties. Okay, so if this were 6.45 minus 2.72, okay, you would still add the uncertainties, even though subtracting the number here is going to give you a different number, right? It's going to give you that, but you still add the uncertainties. In symbolic form, as you would find in a textbook or an appendix, okay, in the IB textbook, you would see this rule written symbolically this way, okay, and if you were looking in the lab manual appendix, the UTA lab manual appendix, you would see it this way. So I'll let you work out on your own how these different ways of representing the rule are actually saying the same thing. We're going to go on to the rule for what if you're multiplying and dividing numbers. Multiplying and dividing numbers. Okay, so let's take a look at an example here. All right, so here I have a number that's expressed in absolute uncertainty times a number that's expressed in percent uncertainty, right? So the first thing you need to do is you need to get both sets of numbers into percent uncertainty. Okay, so what I need to do here is I need to get this number on the left in terms of percent uncertainty. So I need to do 0.2 divided by 8.09. That comes out to 2.5%, so I'm going to go with 3% on that. Okay, and now I can multiply these two numbers together. And let me show you what happens to the uncertainty. Okay, so I'm going to multiply 8.09 times 25, and that gives me 202.25. Okay, so 202.25 plus or minus, and what you end up doing here is you end up adding those percents. So you're going to add the 3 plus the 6, you're going to get 9%. Okay. Now, what you need to do is you need to check, you need to figure out what's 9% of the value, and then you're going to need to adjust the decimal places that you have displayed. So 9% of 202.25 is 18. That means that having precision to the hundredths when I have an error of plus or minus 18 is way off, so I'm going to need to rewrite this to something like this, 220 plus or minus 20, right, like that. Or that would be in seconds. That would be in absolute terms, or I could write it as 220 plus or minus 9%. Right, so I can express it two different ways. Just because I started with percent uncertainty, stay with percent uncertainty, I can express it as an absolute uncertainty as well. But notice how I adjust my final value to match the amount of digits of uncertainty that I have. These have a symbolic representation. In your textbooks as well. All right. Again, here's the IB version. Okay, and here is the AP version. Okay, so when you first see these, you're like, whoa, it's way complicated. But if you see a numerical example, then I think it's very doable. All right. There are a few more rules, like for example, what do we do with powers? Okay, like a square or a square root. The rules for powers or roots. So I got a number here. Okay, they're both in relative percent terms. All right, so let's work this out. We're just combine the numbers like we normally do, right? So 3 squared is 9, and 2 cubed is 8, so 9 times 8 is 72, right? So we end up with 72. And what we're going to do with the error, though, is a little bit different. We are going to multiply the error times the power, right? So this here would be 4, okay? And this here would be 12. And then we're going to add these two together. Okay, so what this is going to come out to is 72 meters to the 5th, right, because I did a square and a cube, plus or minus 16%. Okay, so when you're doing powers, okay, you have to multiply the percent errors. And we do have a symbolic version for this as well, IB version and AP version. Okay. I'll also write out for you the what if you had a square root instead of a square. It's right here. Okay.
Notice that when you're taking a root, okay, you're going to end up dividing rather than multiplying by that power. So if it were, you would divide the fractional error by 2, right? A cube root divide the fractional error by 3. Excuse me, the percent error.
And that, ladies and gentlemen, is error propagation in a nutshell.